So this week's lab will be performing this saponification reaction. So this reaction occurs between a triglyceride and a strong base and forms three soap molecules and a byproduct, glycerol. So in our experiment, we'll be using lard as our fat because we're in the south. Lard is generally used in cooking, and I think it's just pig fat. For our strong base, we'll be using sodium hydroxide. If we wanted to make liquid soap, we would use potassium hydroxide. But anyway, sodium hydroxide, that's commonly found in drain cleaner. It's a caustic substance, which means it attacks and digests organic matter. That makes it really great for unclogging your drain or disposing of a dead body. And so, after carrying out this reaction, we should produce glycerol and soap molecules. Triglycerides, they generally have the same structure, uh, and they always have different R groups. These are generally just really long chains. R group just means it's any carbon chain. So I like to think of it as R means the rest of the molecule. Depending on the structure of the R group, the fat itself could be a solid or a liquid. Generally, saturated fats, those are found as solids at room temperature. This is because the carbon chains, they're really straight and they stack really well on top of each other. So that results in the solid triglyceride. Unsaturated fats, those are usually oils. So these chains, they're not saturated with hydrogens, and where there's missing hydrogens, there's generally a carbon-carbon double bond. And so if you remember molecular geometry, that means these chains are not as straight as single-bonded chains, and it makes it much more difficult for them to stack on top of each other. And so that results in a lower melting point and making an unsaturated fat generally a liquid. So I drew all cis fats here because all the double bonds are in the cis conformation. Trans fats, those are also a type of unsaturated fat, but trans fats don't occur in nature. So generally your body has no idea what to do with them, and so they're unhealthy. But microbes that also make your food go bad, those don't know what to do with trans fats either, and so trans fats preserves food really well. So anyways, back to soap. Soap is considered a metallic salt, which means it ionizes in water. So the sodium ion ionizes from the rest of the soap molecule. The soap molecule has a polar end and then it has a nonpolar tail. Polar end is usually soluble in water, so it interacts really well with H2O, while the nonpolar end, that interacts really well with dirt and grease, and for the most part it sticks to dirt and grease. If you have a lot of soap molecules, you'll end up forming a soap micelle, and so these generally, they'll stick to dirt particles, grease particles, bacteria membranes, or even virus particles. And so the water can easily wash away whatever it's stuck to. So that's what you're doing when you're washing your hands. You're physically, or I guess technically chemically removing dirt particles, virus particles, and things from your hands because the soap sticks really well to it. And then the polar ends wash away really easily in water. So even if the solution is only made up of water and soap, the nonpolar ends, they'll usually try to interact with the only other nonpolar thing in the solution, which would be other nonpolar tails from other soap molecules. So even if you don't have dirt in a solution, you'll still form micelles, just without any nonpolar particles in the center. So in this week's lab, we'll be looking at colloids. So some examples, well, the basic idea of a colloid is, so you have one substance and it's dispersed as tiny particles into another substance. So some examples, milk is an example of a colloid. Fat particles, it's made up of fat particles dispersed in the water. Fat is generally insoluble in water, but because the fat particles are so small, they stay suspended and generally never aggregate. Unless bacteria make the milk too acidic, then you get clumpy milk. But another example are clouds. Uh, those are just tiny water particles suspended in air. We'll be looking at soap solutions. Uh, those are micelles dispersed in the water. And then today, or for this experiment, we'll be doing a hard water test. Uh, so we'll be adding metal ions to hopefully precipitate out the salt. So we'll precipitate the soap out of solution. If you look up hard water tests on Google, like people usually use this to determine if their tap water is hard water. So what they're trying to test is if their water has metal ions in it or not. So if you want to test if your water is hard or soft, what you would do is you would add soap to that water and see if it foams or not. If it's hard water, the metal ions, those will react with the soap, and so the soap won't foam as much anymore. It'll just form a solid, an insoluble solid, and just float around in solution. So in our experiment, though, we're kind of doing the opposite of that, and we're intentionally adding the hard water ions to see if our final product is actually soap. So if it's actually soap, then it will react with the hard water ions and it will stop foaming. And if we have good soap, it'll take a lot of hard water ions to actually make it stop foaming. And we'll also have we'll be testing a control right next to it to see how the prepared soap matches with the control soap. And then the last test that we're doing is the Tyndall effect. So an example of this would be, say, like a laser pointer. Usually you can't see the beam itself until something scatters it, and the photons can actually reach your eyes. Another example is headlights in fog. You can see the beam because the water particles that make up the fog, those scatter the light itself. But if the photons are moving away from the source, generally, if they're not pointed at your eyes, they won't reach your eyes. But because there are water particles scattering the light, that's how the photons actually reach your eyes. Same thing with like blue-colored eyes. So blue eyes, those are a mutation where a person has much less melanin in their iris. That layer should actually be transparent, but the iris itself scatters short wavelength light, and so that's why it looks blue, because blue light is the shortest wavelength. It oscillates really quickly, and so it interacts with the transparent layer much more. So for our experiment itself, we're going to be shining a laser pointer through the soap solution, and also doing that with a control. So the more soap micelles there are, the more it should scatter light. So if we made good soap, there should be a lot of light scattering in this test.